In last video we discussed that when in a free ion the 5d orbitals are degenerate, that is energetically equal. When these d orbitals come in contact with the spherical crystal field, the average energy of the d orbital is increased, but all the d orbitals are degenerate. Here the ligand exert an electrostatic field which tends to repel the electrons, particularly the outer d electrons of the central metal ion. And the d orbitals, they are not same, they are of two types, that is Eg and T2g. Eg orbitals are present along the axis, while T2g orbitals, they are present in between the axis. When ligand approaches towards the central metal ion in octahedral field, they approaches along the axis. So the electrons which are present in Eg orbital and the ligand, they repel each other, so the energy of Eg orbital is increased as compared to the average energy. This is the average energy. So as compared to average energy, the energy of Eg orbitals are increased, while T2g orbitals, that is dxy, dyz and dxz, which are present, whose lobes are present in between the axis, their energy is decreased as compared to the average energy of d orbital. Here you can see the energy difference between Eg and T2g. It is denoted by either delta O, where O stands for octahedral, or it is also denoted by 10 dq. The increase in the energy of Eg orbital, it is of 3 by 5 delta O, or it can be written as 10 into 3 by 5, that is equal to 6 dq, while the decrease in the energy of T2g orbital, it is given as minus 2 by 5 delta O, or it is minus 4 dq. Now, this difference in energy between the two sets, that is T2g and Eg, is given either of the symbol 10 dq or delta O. Now, what is the meaning of 10 dq? Here 10, it is nothing but the number of d electrons. In d orbital, it can accommodate 10 electrons. So 10, it is the number of d electron. Capital D, it is the destabilization of d orbital in presence of ligand, and Q is the charge of approaching ligands. The magnitude of 10 dq or delta O, it is dependent on three factors. One is nature of the ligand, then charge on the metal ion, as well as it depends upon row of transition elements from which the metal ion is there. Don't worry, the detail of all these factors we'll discuss in next video. So before starting the remaining part, let's see some important definitions which we will come across number of times. So first is strong ligand field splitting. Strong ligand field splitting. Now we saw the difference between the energy difference between Eg and T2g. It is denoted by 10 dq. This value, it may be larger or smaller. Depending on that, there are two different types of splitting. One is strong ligand field splitting. If the 10 dq value is larger, it is called strong field splitting, and the complex form are called strong field complex. The second type, it is weak ligand field splitting. If 10 dq value is smaller, then it is called as weak field splitting, and the complex form, it is called as weak field complex. Weak ligand, the ligand which cause only small degree of split, it is termed as weak ligand, while the ligand which causes large splitting are called strong ligand. Okay. Now, based on these, whether they are weak ligand or strong ligand, the common ligands are arranged in order of their strength, and that series is called as spectrochemical series. Here you can see that when we go from here, iodide is there, iodide to water, iodide to water, all these are the weak field ligand, while after water, that is from thioisocyanate to CO, these are the strong field ligand. So the ligands which are present before water, these are weak field ligand. That means they causes a very low splitting, and which causes more splitting is called as strong field.